Our project title is a fuzzy and hybrid algorithm-based optimal placement of DG for power loss reduction and voltage profile improvement. Objective: the optimal placement of DG in a power system is a crucial task to improve power system performance, reduce power losses, and enhance voltage profiles. Combining fuzzy logic with the teaching learning based optimization algorithm and harmony search algorithm is a promising approach for finding the optimal location of DG units. Introduction: the integration of DG has emerged as a pivotal strategy to enhance system efficiency, mitigate power losses, and improve voltage profiles. The optimal placement of these DG units plays a critical role in achieving these objectives, demanding innovative approaches that address the complexity and uncertainties inherent in power system dynamics. This project reveals into a comprehensive methodology that integrates fuzzy logic, the teaching learning based optimization algorithm, and the harmony search algorithm to determine the optimal locations for DG units. This multifaceted approach seeks to strike a balance between power loss reduction and voltage profile improvement, ultimately contributing to the robustness and resilience of power distribution systems. Existing method. In existing method, a combination of two well-known techniques, namely teaching learning, known as teaching learning algorithm, has been used to determine the appropriate sizes and locations of DG in distribution network, considering power loss reduction and improvement in system voltage profile as the key objectives. The TL technique is applied to IEEE 33 bus and IEEE 69 bus. Drawbacks of existing method. Convergence speed. TLBO may exhibit slower conversion rates compared to some other optimization algorithms. The algorithm might require more iterations to reach an optimal solution, which can be a limitation, especially for large-scale power systems or real-time applications. Parameter sensitivity. The performance of TLBO is sensitive to the values of its parameters, such as the teaching factor and learning factor. Selecting appropriate parameter values for different power system configuration and DG placement scenarios can be challenging and may require careful tuning. Limited handling of constraints. TLBO may struggle to handle constraints effectively. In DG placement problems, there are often physical and operational constraints, such as capacity limit, voltage limits, and network constraints. Ensuring that TLBO respects and satisfies these constraints can be a challenging task. How to overcome these drawbacks? To overcome the existing method drawbacks, with combining teaching learning based optimization with harmony search and fuzzy logic controller can be a powerful strategy to overcome some of the drawbacks associated with each algorithm individually. The hybridization of TLBO, HS, and FLC aims to leverage the strengths of both algorithms and enhance their overall performance. Proposed system. The optimal placement and sizing of distributed generators in a power system is a complex task that involves finding the most suitable locations and capacities to minimize power losses, improve voltage profiles, and enhance the overall system performance. Integrating fuzzy logic with a teaching learning based optimization algorithm and harmony search algorithm provides a comprehensive and intelligent approach to address this challenge. The methodology for the optimal placement and sizing of DGs, tested on 33 bus and 69 bus power systems. Inspiration of the algorithm. This algorithm consists of two phases. First one is teacher phase and the second one is learner phase. In teacher phase, all the students learn from teacher and gain knowledge. In learner phase, students interact among themselves to share knowledge with each other. Harmony search. Initialization. Initialize the harmony memory considering possible DG sizing. Harmony memory consideration. Update the harmony memory with the best solution. Generate new harmonies by considering memory and randomness. Evaluation updating. Evaluate the fitness of new harmonies. Update the harmony memory if better solutions are found. Hybridization. Combine TLBO and HS with FLC in a synergistic manner. These might consider using one method as the primary optimizer and the other for fine-tuning or diversifying the search. For example, can use FLC for the primary optimization for placement and DLCHS for DG sizing. Optimal DG location using fuzzy approach. Main objectives considered while designing fuzzy logic is minimizing power loss and maintaining voltage within permissible limit. Fuzzy interface containing set of rules used to determine DG placement suitability of each node in the considered distribution system. At first, load flows are performed to find the real power loss and then performed again to obtain power loss reduction by compensating total real power load at every node of distribution system. Loss reduction linearly normalized in 0 to 1 range. Loss reduction formula. In loss reduction formula, where I is the number of iteration, power loss index for ith node will be, power loss index formula is as shown. The input variables are PLI and per unit nodal voltages. The output variables will be DG suitability index. PLI ranges from 0 to 1, per unit nodal voltage ranges from 0.9 to 1.1 and DGSI will be ranges from 0 to 1. The location having maximum suitability index value is the optimal location for DG placement. The 5 triangular membership function selected for PLI and DGSI are L, LM, M, HM and H, where L means low, LM means low medium, M means medium, HM means high medium and H means high. 5 membership functions which are trapezoidal and triangular are selected for voltage. They are L, LM, M, HM and H, where L means low, LM means low medium, M means medium, HM means high medium and H means high. Fuzzy membership function. Membership function plot for PLI and per unit nodal voltages. These are the two graphs for input variable, and the first one is for power loss index and the second one is for voltage. And here we have considered the triangular waveform for power loss index, and voltage input variable consists of both combination of trapezoidal and triangular waveform. Fuzzy membership function plot for DG suitability index. This is the output variable and this is the table of fuzzy ruler. Fuzzy ruler formed to determine the suitability of a node for DG installation as shown in this table. Based on this table, the suitability of a node for DG installation is determined, where NS means negative small, NB means negative big, Z means 0, PS means positive small, PV means positive big. Fuzzy rule here, as we have considered 5 by 5 rules, there are of 25 rules. Now this first one is for input variable of power loss index and it has triangular waveform, and the second one is for input variable of voltage and it has combination of both triangular and trapezoidal waveform, and the third one is the output variable graph. The color shaded region is the indicates the correct optimal location of the DG. Whenever we move this red line, the region of the color shade varies. By that we can decide the optimal location of the DG. Now I am showing the results of our project. This is the code for IEEE 33 bus. This is the graph displayed after running the program. This is voltage profile for 33 bus system with DG placement using TLCHS, and the x-axis indicates number of buses and the y-axis indicates voltage profile in per unit. And the blue line indicates the voltage profile value before placement of DG, and the dotted green line indicates the voltage profile value after placement of DG. As our aim is to place a single DG, as we consider that there is a more reduction in voltage profile near 33 bus, so we are placing the DG near 33 bus. These are the values obtained by the results. This is total real power loss before DG placement, and this is the optimal location of DG. As we consider to place only a single DG, the optimal location of placement of DG is near 30, and this is the optimal size of DG, and this is the total real power loss after DG placement. Here we can observe the difference before placement of DG and after placement of DG, and this is the percentage of loss reduction. Now I am showing the result for 69 bus. This is the code for IEEE 69 bus. This is the graph displayed after running the 69 bus code, and this is voltage profile for 69 bus system with DG placement using TLCHS algorithm, and the x-axis indicates bus numbers and the y-axis indicates voltage profile in per unit. The blue line in the graph indicates the per unit voltage profile value before placement of DG, and the dotted green line indicates the voltage profile value after placement of DG. Here we can see there is a reduction in voltage profile before placement of DG. So now our aim is to place a single DG, and we have select the place of selecting DG near the 69 bus. After placement of DG, the voltage profile has improved. These are the output values of IEEE 69 bus, and this is the total real power loss before DG placement, and this is the optimal location of DG. As we are considering a single DG placement, the optimal location for placing of DG is near 61. The optimal size of the DG is this, and this is the total real power loss after DG placement. Here we can observe the variation of total real power loss before placement of DG and after placement of DG, and this is the percentage of loss reduction.